All right, we're going to be wrapping up thermodynamics now. We'll be talking about specific heat and enthalpy. So first thing to keep in mind is that different substances have different specific heat capacities. What we need to understand about that is either specific heat or heat capacity as it may be referred to. This indicates the ability of a substance to heat up or cool down. So if I have a very high specific heat, which I'm going to denote as little s, that means that it takes a long time to either heat up or cool down. If I have a very low specific heat value, then it is going to very, very quickly heat up and cool down. That is what specific heat tells us. Now, the heat of a process depends upon the substance's specific heat, S, its mass, which we're going to say is little m, and its change in temperature, delta T. So the way that these relate is the heat energy of the process, Q, is equal to specific heat times mass times change in temperature. So to be clear about one thing here is a change in temperature, this delta T, comes from our final temperature, T2, minus the initial temperature, T1. So in its brief form, the equation that we're looking at here is heat, Q, is equal to specific heat, S, times the mass of the sample, M, times the change in temperature, delta T. So you can kind of break this into two steps. If you know the beginning and ending temperatures, you can first solve for the change in temperature, then plug that in here and solve for the heat of the substance. So to give you an example that is going to make some sense, let's say I give you a water sample, and I want to know how much energy does it take to heat up water from 20 Celsius to 50 Celsius. Now, a couple things that we have to be familiar with here is the specific heat of water is, so this S value for water is 4.18 joules of energy per gram degree Celsius. So what this communicates to us is that it takes 4.18 joules of heat energy to change the temperature of 1 gram by 1 degree Celsius. Okay, so let's be clear about this. Specific heat is always expressed in joules per gram degrees Celsius. It wouldn't make a difference if it was degrees Celsius or kelvins because they're 1 to 1 in the scale. So if we're looking at, let's say, this difference, right, 50 degrees to 20 degrees. You would take T2, 50, minus 20 equals a delta T of 30 degrees C. If these were in kelvins, then it would be this plus 273 and this plus 273. So I'd have 293 Kelvin, and my 50 degrees plus 273 is going to be 323 Kelvin. 323 minus 293 is also 30, but it's 30 kelvins. So it does make a difference. The change could be in either scale. You don't have to convert back and forth. Now, the thing that is missing here is we want to know, I know the delta T, I know the S. Let's say that my mass is 50 grams of water. So I can plug everything into this Q equals SM delta T equation, and I will see 4.18 joules per gram degree C can be multiplied by my mass, 50 grams, and multiplied by the change in temperature, 30 degrees Celsius. Now, note, grams cancel grams, degrees C cancels with degrees C, and I will be left with joules, which is Q, the heat energy. When we do the math on this, let's go ahead and work that out. We're going to see it is 4.18 times 50 times 30. And that comes out to 6,270. So 6,270 joules of energy would be required to heat up 50 grams of water from 20 to 50 Celsius. Now, if a substance is changing from one state to another, instead of energy being used to change the temperature, energy is used to either form or to break the bonds that hold it together. So, in this case, this process is dependent on the mass and the enthalpy of fusion or the enthalpy of vaporization. Okay, so that's a new term, enthalpy. I want to clarify the idea here. Enthalpy, it describes the amount of heat energy required to perform some specific task. So the enthalpy of fusion, enthalpy is denoted as the change in H, indicates, you can think of that as a change in heat, the delta H. So the delta H of fusion, FUS, this describes a specific task, and that task is going from solid into liquid state. So if we're changing states and we're going from solid to liquid, what we would have to know is the heat of fusion, and we have to know the mass that that's being applied to. There is no change in temperature, and the specific heat is a non-factor. So if instead we're talking about the process of vaporization, the delta H VAP, right, vaporization, this is going from its liquid state into a gaseous state. So again, enthalpy describes the amount of heat required to perform a specific task. Now you could actually have the enthalpy of a reaction, and that would be how much heat required to do one full reaction. Okay. Heat of combustion, how much heat to perform one complete combustion. The enthalpy of formation. This is the amount of energy required to form 1 mole of a specific substance. Okay, so enthalpy always describes a specific task that is being completed, and it's the energy change of that task. Now I will go ahead and pause this here, let you work these problems out, and then we will resume this in a bit.